Imagine standing on a coastline, the air just thick with anticipation. You can feel the sheer, raw power of the ocean as these massive waves crash ashore.
Hmm.
It's such a primal force, really a reminder of nature's might, even when the storm itself is like hundreds of miles away.
Absolutely. That energy travels incredibly far.
And that's precisely the kind of visceral impact that many folks along the U.S. East Coast are probably experiencing right now. Welcome, everyone, to the Meteorology Matters podcast.
Glad to be here.
Today, we're taking a deep dive into something that's really been making headlines, even from a distance. Hurricane Erin. It's quite a dynamic, powerful
It
system.
really has been fascinating to watch, meteorologically speaking.
Yeah, it's captivated meteorologists, definitely concerned coastal communities, even from way offshore. And while its current path looks incredibly fortunate for many,
Extremely fortunate.
Erin gives us this crucial, almost textbook chance to understand a phenomenon that seems to be, well, more and more prevalent and concerning in recent decades: rapid intensification.
That's the key takeaway from this event, I think, beyond the immediate forecast.
Exactly. So we're going to go beyond just the latest forecast track for Erin and really explore why understanding these accelerating trends isn't just for weather geeks like us.
Right. It affects everyone.
It's vital for anyone living near the coast, for emergency planners, really for anyone just curious about our changing planet and the forces shaping its climate. And to guide us through this complex but absolutely fascinating and critical material, we have our expert.
Thank you. Yeah, what we're seeing with Erin, it isn't just another powerful storm. It really is a living, breathing example of some pretty significant shifts in our global weather patterns.
Mm-hmm.
So my aim today is really to help you connect the dots, maybe offer some broader context and the scientific underpinning of these incredible atmospheric processes,
Okay.
and ultimately try to understand what it all means for you.
Okay, so let's unpack this, starting with Hurricane Erin itself. It's been, well, truly captivating, if a bit concerning, to watch unfold. From a meteorologist's standpoint, what's the very latest picture, especially considering that really dramatic initial strengthening?
Yeah, you're right to flag that initial strengthening. It was remarkable is probably the word.
Right.
Just yesterday, the atmospheric conditions just converged in this stunning way, really allowing Hurricane Erin to literally blow up into a Category 5 storm.
Just like that.
Pretty much. The speed of that transformation was, well, truly something. It was, in fact, one of the fastest intensifications ever observed.
Wow.
And just to put that into perspective for you, the central pressure recorded when it peaked was extremely low. Astonishingly low, actually. It was the second lowest ever recorded for an August hurricane.
Second lowest. What was the first?
The only storm that surpassed it in August was Hurricane Erin, way back in 1980.
Allen, right. I remember that one.
So this kind of sudden, explosive surge in power where a storm just seems to defy expectations and accelerated strength,
Mm-hmm.
that's precisely the heart of what we mean when we talk about rapid intensification.
Okay.
The environment around Erin was just perfectly primed. We saw incredibly warm ocean water, just loads of fuel,
Right, the fuel.
coupled with very low vertical wind shear. So basically, very little disruption from winds at different heights, which let the storm's structure stay intact and its inner core just consolidate really efficiently.
Uh-huh.
All the necessary ingredients just came together at exactly the right time, creating this stunning surge in strength. Well, it's a stark reminder of the immense energy in these systems when conditions align perfectly.
And crucially, that terrifying intensity, while, yeah, a stark illustration of the phenomenon, it has stayed offshore.
So from a safety perspective, can you elaborate on Erin's projected path? Explain why that specific track offers such a, well, profound sense of relief for so many people. Absolutely, and profoundly is the right word. We are, to put it mildly, extremely fortunate with Erin's track so far.
Okay.
Currently, the storm is tracking about 150 miles offshore of Puerto Rico. But the really critical detail is its projected path over the next few days.
Where is it headed?
Erin is forecast to make a pretty sharp turn north, well before it even gets close to the Bahamas.
Okay, good.
From there, it's going to essentially thread the needle.
Mm-hmm.
It'll split the gap between the U.S. East Coast, specifically around North Carolina, and the island of Bermuda.
Ah, so right between them.
Exactly. And ultimately, its trajectory will take it well out to sea, away from any significant land masses.
Phew.
The large-scale weather pattern that sort of orchestrated this specific path, it's an immense blessing for those densely populated coastal areas.
Yeah, you say that again.
I mean, if this powerful storm had veered even slightly west, closer to the Caribbean islands or the U.S. mainland,
Yeah.
the impacts could have been catastrophic.
Absolutely.
We're talking the difference between a near miss and a direct hit on major population centers. This particular pattern has effectively acted like a giant atmospheric shepherd, steering a truly monstrous storm away from direct land interaction.
Right.
It really is the best-case scenario, given its initial incredible intensity. It means that while the storm is undeniably powerful, and yes, it will bring significant indirect impacts.
Which we'll get to.
Exactly.
Yeah.
But it's not delivering the devastating winds, the storm surge, the torrential rain you get with a direct hit. And that dramatically changes the type of preparation and response needed. It's a huge sigh of relief for millions.
Definitely good to hear it's staying offshore. But I understand it's also undergone some structural changes since it peaked. What's its current status, and how do those changes affect its intensity and maybe, more importantly, its overall footprint?
That's a very perceptive question. It really highlights how dynamic these systems are.
Yeah.
You're right. Erin has weakened somewhat from that peak Category 5 intensity. As of now, it's a powerful Category 3 hurricane. But, and this is important, this change isn't necessarily a sign of the storm just dying out or becoming less of a threat overall.
Right. It's more complex than that.
Exactly. Instead, it's undergoing a very natural, the complex, cyclical process. It's called an eye wall replacement cycle.
Okay, eye wall replacement. How does that work?
So try to visualize a hurricane like a donut. The hole is the eye, right?
Right.
And the donut itself is the eye wall. That's where the strongest winds and heaviest rains are.
Got it.
During an eye wall replacement cycle, the storm develops a new, larger eye wall structure that forms around the original inner one.
Ah, okay. Like rings on a tree almost.
Kind of. And as this new outer eye wall forms and starts to contract, it essentially chokes off the original inner eye wall, causing it to dissipate. Now, this process, as the energy gets redistributed over a larger area, typically causes the peak wind speeds to temporarily diminish, because the storm's energy is being spread out over a larger circulation diameter. Think of like a figure skater. When they pull their arms in, they spin faster, right?
Yeah.
When they extend their arms, they slow down. Erin's doing something similar with its structure, just on a much grander, more powerful scale.
Okay, makes sense.
But what's crucial to understand here is that this doesn't necessarily mean a less dangerous storm overall.
How so?
Well, while the peak winds might drop temporarily, the storm's overall size expands.
Ah, it gets bigger.
Exactly. Which means it will move more water, potentially creating stronger and more widespread storm surge if it were closer to land.
Right.
And generating more significant and broader wave action and currents even far offshore. This process is also notoriously hard to forecast precisely the timing, the exact impact on intensity. It adds another layer of complexity.
So it could even get stronger again.
Absolutely. We actually expect Erin's intensity to fluctuate a bit as it continues these cycles and encounters other factors. In fact, it is forecast to re-intensify again as it turns north well east of the Bahamas, even as it continues to grow in size.
Wow.
This expansion means the storm could still have a really far-reaching influence, even if its core stays way out at sea.
So even with an offshore track and some, temporary weakening, you're saying its sheer energy is still going to be felt far and wide. What are the specific coastal impacts we should be preparing for along the U.S. East Coast and beyond?
Indeed. That's precisely the message we need to get across clearly. Even an offshore hurricane of this magnitude, especially one that's expanded in size like Erin has, puts a tremendous amount of kinetic energy into the ocean.
Just churns it up.
Exactly. And this energy primarily shows up as unusually strong and dangerous currents and large, powerful wave swells which will propagate across vast distances. These impacts will be felt along a really wide range of coastlines, extending from the Caribbean all the way up to Canada, including the Bahamas and the entire U.S. East Coast.
The whole coast, basically.
Pretty much. Let's break down the specifics for you. For Florida and the southeast coast, you can expect these ocean impacts to start showing up as early as Tuesday. The main areas of concern will stretch from roughly Palm Beach County northwards up to the Georgia border. Now, the Bahamas will actually act as a bit of a physical barrier.
Oh, interesting.
Yeah, which helps diminish some of the direct wave energy that South Florida might otherwise get.
Right.
But rip currents will remain a very significant and life-threatening concern for beaches throughout that entire region.
Definitely need to watch out for those.
And the surf will be elevated too, making swimming hazardous. Then, as the storm tracks northward, the peak impacts will shift to the Mid-Atlantic and New England regions. That'll happen primarily on Wednesday and Thursday.
Mid-Atlantic and New England, weathers.
Right. Our computer prediction maps are showing this peak wave energy and stronger current activity focused very clearly between Cape Hatteras in North Carolina and southern New England, particularly during Thursday morning. You'll see those impressive, albeit dangerous, swells rolling in.
Okay. What about wind? Any direct wind impacts expected on land?
In terms of fringe wind effects, so we're talking the outer bands, not hurricane force winds.
Right, not the core.
Exactly. Eastern North Carolina, the Virginia Tidewater region, and maybe the Delmarva Peninsula are the most likely U.S. locations to feel some of those effects. Probably around Wednesday.
Okay.
Now, nothing severe or damaging is expected in those areas, but you'll likely feel a noticeable difference in the wind, a distinct indication that a strong, broad storm is churning offshore.
A reminder it's out there.
Precisely. The good news is, by Friday, Erin should be moving well out to sea,
Mm.
which is excellent news for the weekend.
Ah, good.
This means the weekend along the beaches should look much finer for most areas that felt its influence earlier in the week. Conditions should slowly start returning to normal.
That's absolutely crucial information for anyone with beach plans or coastal activities this week. It really sounds like vigilance is key. So, what's your strongest safety message for our listeners, given these expected far-reaching impacts?
My strongest and most urgent advice is this. Anyone planning beach activities, swimming, surfing, even just wading or any boating activities this week, you absolutely must pay close attention to instructions from local harbor masters, lifeguards, and emergency services.
Heed the warnings.
Absolutely. The currents along the coastlines, I just mentioned, will be unusually strong, unpredictable, and genuinely dangerous till Erin moves well out to sea. This isn't just about the size of the waves you can see. It's about powerful, often unseen currents that can pull you away from shore with alarming speed.
Right, the rip currents.
Exactly. And specifically for rip currents, and this is a critical safety rule that saves lives if you do find yourself caught in one, the most important thing is to remain calm.
Don't panic.
Don't panic.
Huh?
Do not try to fight the current and swim directly back to shore against it. That will only exhaust you. Instead, the correct life-saving action is to swim parallel to the beach.
Parallel, okay.
Rip currents are typically narrow, so by swimming parallel, you'll soon swim out of that narrow current and into calmer water. From there, you can then safely swim ashore.
Swim parallel, then swim in.
Exactly. It's a simple rule, but it is unequivocally effective and can be the difference between a close call and a tragedy. Always check local conditions and respect those warning flags.
Excellent. Truly vital advice. We hope everyone takes that to heart. Beyond Erin, which is certainly grabbing the headlines, are there any other systems out there that the National Oceanic and Atmospheric Administration's National Hurricane Center is keeping an eye on?
Yes, there are a couple of other systems worth a brief mention. We never just focus on the one storm, right?
You're always scanning the horizon.
Always. So, offshore of Cape Hatteras, the National Hurricane Center is currently monitoring what they describe as a low-probability, non-tropical low-pressure system. Yeah, starting out that way. It has a slight chance, maybe 10 to 20%, of taking on some brief tropical or subtropical characteristics today or tomorrow,
Okay.
but it's expected to be quickly swept out to sea. It might briefly become a depression, maybe even get a name, but the good news is it's not expected to affect land at all. It'll be very short-lived if it even develops.
Okay, so nothing major there. What else?
Then there's what many are starting to call the next African system. There's a disturbance currently way out in the far eastern Atlantic.
One of those long track waves.
Exactly. Some, though definitely not all, computer forecast models are showing it could develop significantly by the end of the week. Enough to potentially become a disruptive system down the road.
Where would it be by then?
The National Hurricane Center is currently highlighting a large potential development area for later in the week, when this disturbance is expected to be approaching the Caribbean islands.
Approaching the Caribbean. Okay.
Now, for next weekend, there's currently a significant lack of consensus in the various computer forecasts. It's really all over the place.
Oh!
Some predictions take the system north, kind of following a path similar to Erin's, recurving out to sea.
That'd be good.
Others, however, take it west, directly into the Caribbean islands, which would obviously be a much more concerning scenario.
Definitely.
We absolutely need this disturbance to develop a bit more, get more organized, before the models can offer more consistent and reliable forecasts. They need something more defined to latch onto.
Makes sense.
But I have to stress this. We never, ever discount these kinds of systems automatically this time of year. August and September are prime time for these long-track African waves to develop into major hurricanes.
Right, historically.
Exactly. It's precisely the type of system that can cause significant problems for land masses down the line. So it will definitely bear watching very closely over the next few days.
We'll keep an eye on it.
You know, what's truly fascinating here with Erin, beyond its immediate impacts and current track, is that initial, incredibly rapid intensification.
Yeah, that jump to Cat 5.
Right. And this leads us to a really crucial question that meteorologists and climate scientists are wrestling with. What exactly is rapid intensification? And maybe more importantly, why are we hearing so much more about it now? Especially when we look at the historical context and, the findings from recent scientific studies.
That's a perfect lead-in, because when we talk about a storm blowing up into a Category 5 overnight, it's not just like a dramatic phrase. It's a specific, measurable thing, isn't it?
It is.
So just to make sure we're all on the same page, what is the precise formal meteorological definition that NOAA, the National Oceanic and Atmospheric Administration, uses for rapid intensification?
Right. NOAA specifically defines rapid intensification, or RI as we often call it, as an increase in a tropical cyclone's maximum sustained wind speed by 35 miles per hour or more within a 24-hour period.
35 miles per hour in 24 hours. Okay.
Exactly. And that specific threshold, 35 and 24, it isn't arbitrary. It's a carefully chosen benchmark.
Why that number?
Well, it's critical because it allows forecasters to quantitatively assess and categorize these sudden, dangerous increases in strength. When a storm meets or exceeds that criterion, it signals a significant, swift escalation in the threat level.
Ah, like a red flag.
Precisely. It demands immediate attention and triggers specific protocols for emergency response efforts. It serves as a clear, objective benchmark for when a storm becomes far more dangerous far more quickly, which really challenges our traditional lead times for preparation.
Right.
So it's not just a number. It's a direct indicator of elevated risk to life and property.
That definition really helps put it into perspective. And like you said, it's not just theoretical or a number on a chart. We've unfortunately seen some truly devastating real-world examples of rapid intensification recently. Can you share some of those just to illustrate the profound, often tragic impact?
Certainly. And the real-world impact is, profound and often devastating, leaving communities very little time to react. Consider Hurricane Lee just last year, 2023.
Lee, yeah.
I was
intense.
Astonishing example. Lee went from being barely a hurricane, winds around 80 miles per hour, to a top-tier Category 5 monster with 155-mile-per-hour winds in just 24 hours.
Wow, that's a 75-mile-per-hour jump.
Exactly, 75 miles per hour increase, more than double the RI threshold in just one day. Imagine trying to prepare for that kind of escalation.
Unbelievable.
Then there's Hurricane Maria back in 2017, an incredibly impactful and tragic example.
Maria in Puerto Rico.
That's the one.
Yeah.
Before it devastated Puerto Rico, Maria accelerated from a strong Category 1, about 90-mile-per-hour winds, to a catastrophic 160-mile-per-hour monster in a mere 15 hours.
15 hours, not even a full day.
Not even. The speed and intensity of that strengthening left communities on the island with almost no time to adequately prepare or evacuate. The result was just widespread destruction, a humanitarian crisis.
Terrible.
Ultimately linked to nearly 3,000 fatalities, both direct and indirect. It really stands as a chilling testament to RI's destructive potential.
And these aren't just like isolated incidents from the last few years.
Not at all. The year 2020, for example, that record-breaking hurricane season, 6 of those storms rapidly intensified. Hannah, Laura, Sally, Teddy, Gamma, Delta.
6 in 1 year?
6. And since then, we've continued to see RI play a critical role in some of the most deadly and costly storms hitting the U.S. and the Caribbean. Think about Ida in 2021.
Ida, yeah, Louisiana.
Ian in 2022 in Florida.
Devastating.
And Idalia just last year, 2023, also hitting Florida. These cases vividly show that RI isn't just some scientific curiosity. It is a critical, often underestimated factor in the most destructive hurricanes we face. It directly translates into human suffering and huge economic loss.
Those examples are incredibly sobering, really highlights the human cost. So beyond the sheer power, what are the critical challenges that this phenomenon poses specifically for communities and for the meteorologists and emergency managers trying to protect them? Why is rapid intensification so uniquely concerning?
Well, the challenges are multifaceted and incredibly serious. They really stretch our preparedness and forecasting capabilities right to their limits. Firstly, and maybe most critically, it creates immense difficulty for the public response.
How so?
When a storm undergoes rapid intensification, especially as it nears land, it just compresses the timeline for critical decision-making.
Right, you have less time.
Much less time. People in the storm's path are left with very little time to make life-saving choices. Should they evacuate? Is there even time to evacuate? Can they secure their homes? Is it safer maybe to shelter in place now? That window for critical action just shrinks dramatically, often from days down to mere hours.
Yeah.
A storm that looked like a manageable Category 1 might suddenly become a devastating Category 4 overnight. It catches communities completely off guard, leaves insufficient time for people to follow safety protocols. This sudden escalation can lead to delays in evacuation or even make it completely unsafe to evacuate, putting lives at extreme risk.
That's terrifying.
Secondly, it presents significant forecasting hurdles for us, for meteorologists. It amplifies what's already a really complex task.
Intensity forecasting is hard anyway.
Yeah, exactly. Predicting the exact intensity of a tropical cyclone, especially its peak winds, and how it behaves during rapid changes is arguably one of the hardest parts of hurricane forecasting. When a storm is rapidly intensifying, that challenge is amplified exponentially.
Why is it so hard to predict?
Our current numerical weather prediction models, they're constantly improving, but they still struggle to accurately capture the really fine-scale atmospheric and oceanic processes that drive our eye.
The details matter.
Immensely. So this makes it incredibly difficult to predict how severe the storm will actually be when it makes landfall, or even when it's still offshore but impacting the coast like Erin is. This uncertainty then cascades down to emergency managers.
Right, they need accurate forecasts to plan.
Absolutely. It makes it far harder for them to adequately prepare resources, determining evacuation routes, figuring out shelter capacity, pre-positioning medical supplies, deploying first responders. They're essentially planning for a moving target that's accelerating its power at an unprecedented rate, often with less than 24 hours notice for the most dramatic shifts. And the bottom line, the undeniable truth, is that the most damaging and destructive storms, the ones causing widespread devastation, catastrophic economic losses, tragic loss of life, they very often exhibit rapid intensification at some point in their life cycle.
So RI is a hallmark of the worst storms.
It often is. It transforms what might have been a manageable weather event into an extreme disaster, frequently with little warning for those directly in its path. This makes it a phenomenon that demands our utmost attention, understanding, and frankly, investment in improved forecasting and preparedness.
So if we look beyond these individual storms and look at the bigger picture, the trends, what does this all mean? When we look at the scientific data, is this rapid intensification something that's always happened with this frequency and intensity? Or are we truly seeing a new, statistically significant trend emerging in our climate?
That really is the million-dollar question, isn't it? And fortunately, recent, very rigorous scientific research has provided a pretty clear answer.
Oh yeah, what did it find?
There was a comprehensive study that meticulously analyzed an extensive data set, 830 Atlantic tropical cyclones, spanning a significant period from 1971 all the way to 2020.
That's a lot of storms over a long time.
Exactly. And this research wasn't just a casual observation. It was specifically designed to definitively confirm what many scientists had suspected for years. These trends are not just anecdotal. They're not simply within the realm of natural variability.
They're real.
They are statistically significant and represent a fundamental shift. The scope was broad, looking at basin-wide changes in the Atlantic, providing a truly comprehensive assessment of how these storms are evolving over decades. It's about finding the signal through the noise,
Right. And what did that comprehensive assessment find? Can you quantify this increase for us? Maybe starting with the likelihood of a storm, say, becoming a major hurricane really quickly.
Yeah, the findings are stark, quite frankly, alarming. Leaves very little room for ambiguity.
Yeah.
The study highlighted a dramatic increase in what we call major intensification.
Okay, what's that?
That means a storm powering up from a Category 1 or weaker hurricane to a major hurricane, which is Category 3 or stronger, in just 24 hours.
Cat 1 to Cat 3 plus in a day.
Exactly. In the last 2 decades, specifically 2001 to 2020, storms were more than twice as likely to undergo this kind of rapid escalation compared to the earlier period.
More than twice as likely.
Yep. To put numbers on it, it happened 8.1% of the time in that modern era, compared to only 3.2% of the time during the historical period from 1971 to 1990.
Wow, 3.2% up to 8.1%. That's a huge jump.
It's a truly significant increase, a doubling of that specific risk in just a few decades. But it's crucial to understand it's not just these most extreme major hurricane cases that are changing.
Okay.
The research found that storms, just in general, are intensifying faster than they used to across various time windows.
So average intensification is up too.
Yes. When we look at the mean maximum intensification rates, basically the average fastest intensification a storm achieves over a given period, the numbers are striking.
Give us some numbers.
Okay. For 12-hour windows, the mean intensification rates increased by nearly 29%, went from about 12.2 knots historically to 15.7 knots
Big
recently.
knots. That's about 1.15 mile per hour, right?
That's right. So that's an increase of about 4 miles per hour in the average 12-hour intensification speed. For 24-hour windows, the increase was over 27%, from 17.7 knots up to 22.5 knots. That's nearly 6 miles per hour faster on average over 24 hours.
Still significant.
And for 36-hour windows, we saw an increase of over 26%, from 21.3 knots to 26.9 knots. These aren't minor fluctuations. These are average systemic increases across the board. It indicates a fundamental shift in how quickly storms gain strength.
So it's not just the outliers getting more extreme, but the average storm is also getting stronger, faster. That's a big shift itself. But what about those truly extreme, potentially most damaging intensification events? Have those seen an even more pronounced increase? Because that seems like where the most devastating impacts often come from.
You're absolutely right to hone in on that. And yeah, it's here that the findings become even more concerning. The rarest, but potentially most damaging intensification events, what we sometimes call the 99.5th percentile.
A really extreme end.
Exactly. The most powerful, sudden increases that historically occurred almost never arrive. Those have seen even more pronounced increases. This is where the most devastating impacts often originate, precisely because they're so hard to anticipate and prepare for.
So how much have those increased?
For these extreme events, looking at 12-hour windows, intensification increased by over 16 knots. For 24-hour windows, also over 16 knots. And for 36-hour windows, these extreme events saw gains of over 20 knots.
Wow. So the worst are getting even worse, faster.
That's what the data suggests. It means the most powerful, sudden, and therefore most dangerous increases in storm strength are becoming not only more common, but also significantly more extreme in their magnitude.
Okay.
And it's not just about the absolute rates. The probabilities of exceeding certain dangerous thresholds have also gone up significantly.
Like the odds are higher now.
Exactly. It has become statistically more likely for storms to exceed specific intensification rates over time. For example, the probability of a storm intensifying by 50 knots or more within 24 hours.
50 knots, that's Cat 1 to Cat 3 territory.
Roughly, yeah. That probability grew from a low 2.6% in the historical era to 7.4% in the modern era.
2.6 to 7.4. That's almost 3 times more likely.
Approximately 2.8 times more likely, yes. Similarly, an even more extreme 65-knot intensification within 24 hours, that's like going from a Cat 1 to a strong Cat 4.
Huge jump.
That's now about 4.9 times more likely than it was historically. These aren't minor shifts. They are statistically robust, highly significant changes that really demand our urgent attention and adaptation.
And that's reflected pretty starkly in the Saffir-Simpson categories, too, isn't it? Storms are just jumping categories much faster than they used to, which again just shrinks that critical preparation window.
That's absolutely correct. It's a direct consequence of these accelerating intensification rates. Modern tropical cyclones are now more than twice as likely to jump from a Category 1 or weaker storm to a major hurricane Category 3 or greater within just 24 or 36 hours compared to historical periods.
Twice as likely in 24 or 36 hours.
Right. And if we look at an even shorter, more compressed 12-hour window, that likelihood becomes more than 3 times as great.
3 times in just 12 hours. Wow.
It's a profound increase in the speed at which a relatively manageable storm can transform to a catastrophic threat.
And the statistics back this up strongly.
Very strongly. The statistical significance of these findings, from a scientific standpoint, is paramount. The study's analyses were so robust that they suggest it would have been, and I quote, statistically impossible to observe the sheer number of these rapid intensification events we've seen in the modern era if the underlying rates of intensification had not fundamentally changed from historical periods.
Statistically impossible. That's a strong statement.
It is. It means this isn't just a fluctuation within natural variability. It's a clear, observable, and statistically undeniable trend that falls outside the realm of what we'd expect based on the last half-century of data.
So connecting this to the bigger picture,
Yeah.
it really shows that the hazards our coastlines face are truly evolving.
They absolutely are.
This raises the really important question: what's driving these alarming fundamental changes in how quickly hurricanes can power up? It feels like every conversation about powerful weather events eventually circles back to the ocean. Is that truly the case here? Is the ocean the primary driving force?
It is absolutely foundational. The ocean isn't just a driving force, it is the critical fuel source for strengthening storms.
The fuel tank.
Exactly. To understand why, you have to think of tropical cyclones as these incredibly efficient, massive heat engines. Their fundamental process is transporting excess warmth from the oceans and the atmosphere up to higher latitudes, releasing immense amounts of energy as they do it.
Okay. Heat engines fueled by warm water.
Precisely. And here's where the broader context, the global picture, becomes critically important. A staggering 90% of the excess warming caused by human activity on this planet has gone directly into our oceans.
90%.
90%. This isn't a theoretical projection. It's an observed, measured reality. We have unequivocally seen a measurable increase in ocean temperatures, not just at the surface, but extending down to significant depths, what we call ocean heat content, or OHC.
So it's not just skin deep.
Not at all. This OHC provides a deep reservoir of energy for storms to tap into. The average global ocean surface temperatures have increased by about 0.88 degrees Celsius from the pre-industrial period 1850-1900 up to 2011-2020.
Almost a full degree Celsius.
And a truly significant chunk of that warming, 0.60 degrees Celsius, has occurred just since 1980.
Most of it recently.
Yes. And this year, for instance, we've seen oceans setting heat records month after month. It reinforces the idea that temperatures are genuinely off the charts, well beyond historical norms.
So the link seems pretty clear then.
The conclusion is compelling and points to a direct causal link. The simultaneous observed increases in extreme sea surface temperatures and the documented maximum tropical cyclone intensification rates strongly suggest that human-caused warming has already had a measurable, detectable impact on how fast these storms strengthen.
Warmer ocean, more fuel, faster intensification.
That's the core principle. A warmer ocean means more available energy for these heat engines, allowing them to spin up and intensify at speeds we really haven't seen with this frequency before. It's a direct, undeniable link between the warming planet and the increased hazard we're observing.
So warmer oceans are feeding these monster storms, giving them more fuel to intensify faster. But what about where these storms are intensifying most rapidly? Has there been a noticeable shift in the geography of rapid intensification across the Atlantic basin? Because that would have huge implications for different coastal communities.
Yes, that's another incredibly significant finding from the research. And it absolutely has critical implications for how different regions are affected and how we need to adapt our preparedness.
Okay, so where is it happening more or less?
The locations where tropical cyclones are most likely to undergo their most rapid strengthening have indeed changed over the past few decades. Interestingly, there's a noted decrease in the likelihood of tropical cyclones undergoing their most rapid strengthening in the Gulf of Mexico.
Oh, a decrease in the Gulf. That's surprising.
It is a bit counterintuitive, perhaps. While storms certainly still form and impact the Gulf, and can be devastating, the fastest, most extreme strengthening events are becoming statistically less likely to occur there compared to historical periods. It doesn't mean the Gulf is safe from our eye, just that the highest probability seems to be shifting elsewhere.
So where is it shifting to?
Conversely, and this is the concerning part, we are seeing significant increases in the likelihood of rapid intensification along and east of the U.S. Atlantic coast.
Okay, right near the East Coast.
Yes. Also in the tropical eastern Atlantic, that main development region for those long-track hurricanes.
Where they often start.
Exactly. And also in the southern Caribbean Sea.
Southern Caribbean too. Okay.
This geographical shift has profound direct implications. For the U.S. East Coast, for instance, it means an increased threat from storms that can suddenly explode in power closer to shore, leaving even less time for preparation.
Right.
And this region is already grappling with other evolving storm hazards, like slower-moving storms dropping more rain and changing storm tracks bringing unexpected impacts.
So it's compounding the risks there.
It seems to be. And consider the devastating potential for relatively resource-poor Central American nations.
Yeah.
When storms rapidly intensify in the southwestern Caribbean Sea, often very close to land, it can create catastrophic impacts with minimal warning. We saw this horribly exemplified in 2020 with hurricanes Eta and Iota.
Eta and Iota, right. Late season storms too.
Very late season, in November. Both quickly intensified into major hurricanes just as they approached the coast of Nicaragua, causing immense destruction, landslides, widespread loss of life in an area with limited infrastructure to withstand that kind of sudden onslaught. So these spatial shifts mean different communities are facing new and heightened threats, really requiring a reevaluation of long-standing risk assessments.
Here's where it gets really interesting and maybe a bit daunting. You've laid out the evidence so clearly. Storms are intensifying faster, more frequently, and in new places, all fueled by warmer oceans. So, what are the broader implications of this? How do we prepare? How do we adapt to these changing storm patterns? It sounds like we're not just dealing with stronger storms, but also more unpredictable ones, potentially closer to home, shrinking those warning windows.
You've hit on the core, yeah, the existential challenge we face. These findings underscore the urgent, profound need for a much better, more nuanced understanding of these changing intensification rates.
We need to catch up.
We do. It fundamentally redefines the difficulty in accurately forecasting and effectively communicating the increasing hazard to the public. Those traditional lead times for evacuation or preparation, the ones communities have relied on for decades, they're simply shrinking, often to impractical timescales. This really necessitates a radical rethink of our entire approach.
So, what does that rethink look like?
It leads us to a dual necessity, really. A two-pronged approach we have to embrace simultaneously.
Okay.
On one hand, there is the undeniable, clear, urgent need to curb carbon emissions globally.
Addressing the root cause.
Exactly.
Yeah.
Limiting future warming is essential to mitigate additional, potentially even more drastic changes in intensification rates down the line. If we continue on our current emissions trajectory, we can expect these alarming trends to persist, potentially worsen. This is about preventing the problem from escalating beyond our capacity to adapt.
Makes sense. What's the other prong?
On the other hand, we have the equally vital and immediate need for robust emergency preparedness plans and resilience measures. These have to allow our coastlines to adapt to the storms that are already exhibiting these increased strengthening rates and will continue to do so in the coming decades, even with mitigation efforts underway.
So, adaptation for the change is already happening.
Precisely. This means investing significantly in resilient infrastructure, elevating homes, hardening critical facilities like hospitals and power grids. It means continually improving our early warning systems, making them faster, more precise. It means refining and practicing evacuation protocols to account for these compressed timelines.
And public awareness, too.
Absolutely critical. Comprehensive public education campaigns so that every individual understands the increased risk and knows exactly what to do when a storm intensifies unexpectedly quickly. It's about building a more resilient future against a hazard that is actively, measurably evolving right now. We cannot afford to address one without the other. Mitigation and adaptation have to go hand in hand.
That's a truly powerful and actionable message. So, just to recap our deep dive today, Hurricane Erin, now a Category 3, has fortunately stayed offshore for populated areas, but its energy, its power, will still be felt along U.S. East Coast beaches, dangerous currents, powerful waves. Definitely be careful out there.
Please do.
Critically, Erin's initial dramatic strengthening was a prime example of rapid intensification. We learned this phenomenon is now more than twice as likely to occur than it was just a few decades ago, making storms more dangerous, less predictable.
A significant data-driven trend.
And this increase is largely driven by warming oceans, providing more fuel for these powerful systems. And it's not just the intensity, the very locations where this rapid intensification is occurring are shifting, presenting new and heightened threats, particularly to the U.S. East Coast and parts of the Caribbean.
Indeed. The data clearly indicates a measurable impact of human-caused warming on how fast these storms strengthen. It really underscores the urgency of both global mitigation efforts and those localized adaptation strategies we just talked about. These aren't just scientific curiosities. They are real-world changes demanding real-world solutions.
And as we wrap up today's Meteorology Matters podcast, I want to leave you, our listeners, with maybe a thought-provoking idea to consider. Given these changing patterns of storm intensification, their shifting movement, how might our very understanding of hurricane season itself need to evolve as it just dates on a calendar anymore? What does this mean for how we live, build, and plan along our coastlines, not just for the next storm, but for the next generation? It's a critical question for our future resilience and one we all need to continue exploring.
A very important question indeed.
You've been listening to the Meteorology Matters podcast. For more insights and updates on weather phenomena, you can follow meteorologist Rob Jones on Instagram. He's at meteorologist.
That's meteorologist?
On TikTok, he's at TV meteorologist.
TV meteorologist.
And on YouTube, just search for Rob Jones Hurricane. That's Rob Jones Hurricane, where you'll also find the Meteorology Matters podcast playlist with our past discussions. Thank you so much for joining us for this deep dive into how the world and its weather is changing around us.